So potential is different from potential energy because potential is telling you kind of the possible potential energy there will be. Okay, so this is kind of strange. Let's say that you have your ground here, and you're thinking about this location, which is 10 meters above. Okay. Now, you haven't actually thought of what kind of object you're going to put up there, but you just want to figure out a quick way to figure out potential energy should you know what the weight is. And so you know that the potential energy is going to be m times g, and this again is the force of gravity, times the height, which is 10. Okay, so what we're doing here is we're going to first basically figure out, I know my g, I know my h, I just don't know my m yet. So what I can do is I could think that, okay, the potential energy is going to be whatever my mass is times 9.8 times 10, which is 98. Now this is a quick formula to figure out potential energy per mass. I just don't know my mass yet. And so we would say the potential for gravity is 98. We just haven't included our mass yet. So it's the same for electric potential. When we talk about volts, what we're talking about is this idea. We're going to have potential energy equals Q times E times the distance in x. But this is going to be almost identical to the situation over here. We're oftentimes going to know E and the change in x, but we don't know the Q yet, or we purposefully leave it. So we're going to divide by Q on both sides. And this right here is kind of like the 98 on the other side. This right here is going to be our voltage. And so, actually, we normally replace this side over here, and we call that the V. Okay, now one way we're going to use this later on a lot is we're going to be doing the change in volts over change in the distance equals the energy field. That's one way to be working with potential. The other way to think about it is it's work per unit charge. So, like back up here, this potential energy is actually the same as work. And we said that on either side it's actually potential. So this is another way to write it. And sometimes you'll want to use it where you multiply by Q on both sides. Q times the potential. So there's a couple of ways to rewrite this to make it useful. But the overall idea is we haven't actually put a charge through the situation. For example, if we had a battery with a certain voltage, we haven't actually started putting a current through it. We haven't put any charges through the circuit, but we know the difference in potential. So let's do that as an example. So for example, we have a 9-volt battery. Okay, let's figure out what is the amount of work to put one electron from the negative side to the positive side of the battery. And so simply to figure out the magnitude of the work, we're going to be doing W equals Q times the volts. Okay, the charge of an electron is negative 1.6 times 10 to the negative 19th, and then the volts are going to be 9. And so we can figure out exactly the amount of joules being done by moving the current through a circuit. And the total work done here is going to be negative 1.4 times 10 to the negative 18th joules. Now during a calculation, that comes out to be approximately 8.75 electron volts. And this might make sense a little bit more why we call them electron volts, because here we had an electron, here we had the volts. Okay, so let's do another example that has a bit more application. We're going to be looking at an old TV called a CRT. TV, a cathode ray tube TV. So the idea was that there would be, in a cathode ray tube, a positive and a negative potential created by using charged somethings. The distance between those two charged plates would be L, and you're going to be shooting a negatively charged particle, an electron, through a tiny hole in this setup. And I just realized I had these backwards. If we want the negatively charged particle to be going out this way through small holes in the plates, we need to make sure that we are going towards the positive charge. So it would be accelerated along that length, and then it would shoot out, and that was how the TV worked. So the CRT has a voltage of 15,000 volts, the potential between those plates. So the question is, what is the speed of the electron as it leaves? Okay, there's a couple parts to this. We have to think about the change in the energies. Kinetic energy, potential energy initially, and then we have to think about the kinetic energy and the potential energy in the end. Alright, so let's assume that the initial speed of this electron we're shooting through is 0. So the kinetic energy initially is 0. Okay, and along the same lines, once the electron is shot out of this electric field that's going on here, then we would have no more potential energy involved. So the trick is now, we know that the kinetic energy is going to be 1/2 mv squared. What's the potential energy of this? And so looking back at all our equations here, which is going to be most useful? It's going to be this right here. Now, please remember that potential energy and work are very closely related. They're actually almost identical in magnitude. They're just opposite signs. So, right here, we're going to say that the potential energy is actually Q times the charge. I'm sorry, the charge times the potential. And that will give us the amount of joules. So when you need a potential energy and they give you volts and a charge, this is how you can do it. So we need to find the actual velocity. What we're going to do now is solve first. So we're going to times by 2, divide by m, square root, and that right there is going to give us the total velocity in the end. So I have to plug in all my numbers. Q is going to be 1.6 times 10 to the negative 19th. The voltage, the volts are going to be 1.5 times 10 to the 4th. And the distance, oh my goodness, I forgot. Or I'm sorry. Not the distance, the mass is going to be 9.11 times 10 to the negative 31. If you work that all out in your calculator, you should get 7.3 times 10 to the 7th meters per second. So that's 7. 1, 2, 3, 4, 5, 6, 7. 73 million meters per second. I looked it up. That's about 24% of the speed of light. That's pretty fast.